Alrighty, so I'm going to talk about going from 2D geometry to 3 dimensions. It only occurred to me, and probably last night as I was preparing for this in my head, a lot of this could probably be knowledge that could be used in drafting classes, AutoCAD classes, and then with 3D printing becoming the future of manufacturing, I wonder if there could be something done with that. Now, I know nothing of 3D printing, first of all. But I just wondered, where it could go from there. So, if we could please. So what I'm going to talk about today, I'm going to talk about 2D plus CNC toolpaths. So again, I'm going to go from 2 dimensions, and then periodically I'm going to slip into a 3rd dimension. If I do so, I'm just going to change planes. Where we use AutoCAD, a lot of us look at the XY plane periodically, and look at the 3D software, I'm going to go to the XZ plane, for example. And in doing so, I'm going to create these step layers that says it somewhere in there. I'm going to do my top layer, and then I'm going to step down a layer, and I'm going to move out, I'm going to do some machining, and then I'll move down from there. The goals were to build and create a variety of neck profiles and links. What we do right now is based on a standard geometry. I can pass this one around. You can see this kind of a V-neck shape to it. Both of these have kind of a V-neck shape to it. This is one of the profiles available. Another one of the reasons why I did this thing was to create a different neck entirely. I'm sorry, I'm moving around here. This neck was my motivation for doing this. This is actually for a short scale base. So this is not a guitar neck, this is actually a short scale base neck. And I chose that because we didn't have one. One didn't exist. And so I asked the question, can it be done? And that's really what I set out to prove, is whether or not it could be done. I wanted to understand guitar necks. I wanted to take a look at it. And what I found, it shows up in the next slide, is that it's really pretty simple. It's not as sophisticated as you may think if you haven't looked at it. Wait, go back, there's one more point there. And then learning more about 3D toolpaths. Now, before I go on to all this stuff, I want to say that if I have learned anything, it is from standing on the shoulders of giants, right? I think I said that. So, when I start the process of developing toolpaths for a neck, the first thing I did was I took an existing toolpath and I deconstructed it. The first thing that I did. I will also say, why do I do this? Why do I climb the mountain? Because it's there. I created this thing because I wanted to know. I wanted to know if it could be done. Now that I know it can be done, the opportunities are endless. So if you would please. I started with a guitar neck. Again, we didn't have one. We had guitar geometry. We didn't have bass geometry. Certainly didn't have a short scale bass geometry. And so I went after it. When I started to analyze the neck and look at how it broke down, you'll see this in the next slide when we get there. There are only a handful of key contours that we need to be focused on. And it's different when you get things like a guitar body or something even more involved. That's one of the reasons why the guitar technique is a good place to start. In order to make this happen, I focused on AutoCAD as my 2D software. I've been teaching AutoCAD for years. I've used it on my industrial career, so I'm quite comfortable getting around AutoCAD. But AutoCAD, as strong as it is in 2 dimensions, is not necessarily as savvy in 3 dimensions. It doesn't function quite as good as some other software. The software that we use in-house is Rhino software. There's other packages out there. SolidWorks is one that has some exposure to, and I imagine it would function about the same. So whatever your software preference is, the availability is there. You can probably do everything in 3D software. I use AutoCAD because I'm fast at AutoCAD, so I can do it, I can bring Rhino and do what I need to do, and then move on from there. To take all of this software and bring it to that bottom idea, that CNC router, you need a link between the two, computer-aided manufacturing. And so we have a software package which is able to take the DXF files that I can spit out with AutoCAD and Rhino and actually translate that into something that my CNC router can use. We have an axes router is what we call that. So the basics of a neck, it comes down to 4 contours, 4 geometries. One of which is the neck pocket. When you design that neck pocket, pick up any guitar and look at the back of it. I guess acoustic's a bad example because they have a heel on it. You can see a contour in it, something that's not within the pocket itself. Most of them are just hemispherical. I'll explain why you have the blue tail here in a minute. So I've just the red contour, the yellow contour, the green, and then that light blue are the ones that we're looking at. So on the other end of the guitar, from the neck pocket, we've got the headstock, and so you have some contour at the end of the headstock. So that's our light blue curve right there. As it happens, those 2 are actually in the same plane. Pick up a guitar neck and look at it. Look at these samples here. They exist in the same plane. So the other 2 that exist, I'm calling them the transitions. So where we go from our neck pocket to these long runs, or from the headstock to the long runs, I call them the transition points. 4 curves. That's all it boils down to. So once you have identified the fact that I only got 4 curves, then we need to choose them. Which 4 curves are they going to be? We need to decide what we want. So let's talk about neck geometry first of all. I chose Warmouth as an example here. This is an aftermarket guitar parts manufacturer. They sell a lot of stuff, good quality products from what I understand. I'm not here to endorse them necessarily. The reason I chose this is that this talks about their neck profiles. They have 3 of about 30 shown on this particular slide. As I was saying before, our standard has more of a V shape to it. There are many that have C shapes. There are some that are more flat, some that are thicker, some that are wider. It really depends on what you want. If you come down to preference, you can have an asymmetrical neck. They're starting to build those things nowadays. Because again, we're dealing with the neck and it's relatively simple geometry, when I get to the end, to the further learning slide, I'll talk about some of the challenges you have when you try to transition from one type to another. What I'm saying is everything that I'm working with is lines, but if you have some that are curves and some that are lines, getting between them is kind of complicated, but I'll get back to that. So the other 2 of the 4 curves that we need to make sure that we have defined are these 2, the neck pocket geometry and headstock geometry. If we're all using the same neck pocket geometry, then we pretty well have a good handle on what that looks like. The headstock is really up to you, whatever you want it to be. Headstocks, they could be a symmetrical contour, and they may not be. In this particular case, you can tell it's asymmetrical. And then what we get to do is to map them out, start laying them down with respect to each other. Now, I should point out the fact that all along that the 3 slides we looked at with 3D stuff, I have all these lines in here, but at this point the lines don't really exist. I'm sharing them with you for the sake of communicating this is what we're getting to, okay? So we have our heel pocket down here, we have our headstock over there with the 2 transitions. What I have done, I worked in AutoCAD software to get the neck pocket and the headstock where I wanted to. I also drew the appropriate curves for the other transitions, but then when I went to Rhino, or the 3D software I used, I was able to rotate them into position. Effectively, what you have at that point are the contours of the actual neck itself. But remember, that's not what we're building. Now, I said earlier when I started off this presentation, I think that there's some potential to use this kind of stuff in 3D printing. I can effectively draw the neck at this point, but that's not what I want. What I want is the tool that makes the neck. What's important about our tool is that it's a round tool, and the radius of that round tool is the distance away from the component where the center of that tool needs to be. And whenever we create our tool paths, we call them center paths. So the center path of the tool is such that the radius of the tool is going to do the machine that we want to do. And so in order to make that happen, we have to offset. So we have this edge of the drawer, we offset that at distance. Now, I want to caution to you. If you're comfortable in AutoCAD like I am, you think offset, immediately you think of a circle. If you offset a circle, it affects both the X and the Y dimension. Don't do that. In some of these cases, if I was to offset this, for example, this actually does work in the X and Y direction. If you offset this is actually in the XZ direction, you're going to have impact in the vertical, which we don't want. So you need to be cognizant of what you're doing. What exactly are you doing? We want the tool to be away a given distance, and so we've actually split this curve, this contour, and separate it in the X direction. They're moving it away from the Y axis. I will also point out, given this particular picture here, this is a neck profile geometry. It doesn't matter if it's up near the headstock or down near the neck pocket. That's not what's important. What's important about it is that the one that's in the middle is the original geometry itself. That is not one arc, although it may look as such, and they were joined to be one arc at one point. My point is that the geometry is not as simple as having a starting point here with one radius. You understand? There's actually 2 arcs. Well, there's one arc and not mirrored in. Something that you just may not realize when you start to draw it up. So I just want to point that out to you. So we separated it. We got the beginnings of our tool paths. So this slide here, this is the first one where I'm showing you all those 4 contours. I have the separated, I have the offset set up, but I don't actually have the lines drawn in. So remember, here's our guitar right here. This is the headstock, this is the headstock transition, the neck pocket transition, the other transition to the headstock over there. So I'm trying to remind you where you are. I told you that what I'm doing is I'm doing this in steps. So I start at the very top, what would be the layer parallel to the neck pocket and the headstock. And then at every stage, once I've done one round, I'm going to go down a layer, if you will, and I'll do the next one over. For these that I've done, I chose a number of about 40 to 45 layers. And I did that based on the people that had done it before me. And it was pretty good, so I went with that number. Now, about 40, 45 layers and about 3/4 of an inch seems to work out pretty well. Remember, folks, I'm also working with wood. So you also have sanding that comes along with it. So, you know, it makes it a little bit forgiving in that regard. You want higher resolution, you want to do less sanding, more layers, right? So if you want to speed up the process, for example, over-processing, right? Spending more time than you need to. I'm doing one-offs. I just want to know if it can be done. So I was willing to spend 3 hours on the machine to let this thing run. You have a question?
Just a quick one,
Sure.
to make sure I'm understanding before you go further. So you're basically saying on the Z-axis, you're only coming down about 200 of an inch.
Oh, absolutely.
Okay,
a few
okay.
thousandths. Every pass is just a few thousandths, 1.5 pass. So something I think I failed to mention in there. I thought it was in there. I had my 4 contours. One of the things that I did was I divided my contours. I divided them into the actual layers. Maybe I haven't got to that point yet. No? Go back. One more. Okay, I didn't talk about it, the dividing process. We had the contours, I split them, I moved them to account for the tool set, or the tool offset. The next step is also important. I'm going to physically divide it. I take a curve, and using AutoCAD or a 3D software command, I divide it into even increments. Now, what's important about that is that all the curves have to have the same number of points, so that we have an even number of layers as we go down. I had some flubs along the way. I had 40 curves, or 40 points on one curve, 40 on the 45 on the next, and it didn't work, for example. The other thing that I want to point out is the divide command in AutoCAD, for example, is a really good choice. One of the first things that I did that was a bad choice, let's say this was half of the neck profile. The first time I did it, I divided it this way. I just focused on the Z dimension. And what I found was that the machining wasn't as consistent as I wanted it to be. So instead, if I did this curve into 40 increments instead of 40 along just the Z-axis, I got a lot better, more consistent contour. Now, then it gets easy. You've done pretty much the hard work at this point. It's understanding what you want, defining, acting with purpose, getting those curves there, accounting for the tool. After that, you just got to join it all together. I've got 4 sets of curves, and I can easily draw a line from one point to the next, connecting each of these sets of points. I told you earlier I was going to talk about the blue tails on why they go further than they do. Our curve is way up here. The reason that we do that is because we're making step layers. I'm going to go all the way around the component. I'm then going to come down and go all the way around the component again. Every time I jump up and go to the other side, I have to have clearance above my component. And so while my blue lines might have ended right about here, I have them extending to 1/8 inch above the surface. Now, it looks like they're going quite a distance, but that's because of the angle of approach to these blue lines. When you get towards the neck pocket, for example, the angle of approach is rather low. Whereas when you get to the headstock, the angle of approach is quite a bit larger. And so in order to make these extensions to get just above the component, now I'm not even really talking about my lean-ins and pull-offs just yet. In order to do that down here in the headstock, it's shot pretty close to our origin, which is pretty far down here. Okay? That's why they look as long as they do. That's the blue lines themselves. Above and beyond all that, jumping from one side to the other, that's my black lines that I have there. Add the lines, add the arcs as necessary to drive the tooling then up and across and then back down again. I left the points in here for communication's sake so you can see. I put them in there whenever I'm drawing it so I can keep track of where my start and my end point are, but I left them here for the sake of what we're talking about today. I'm going to start here, I'm going to come in and stay close to the crown, if you will, the peak of the neck. I'll go in, I'll make a pass, I'll come around, I'm going to loop around and go around, 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 around. So on this end, my lines are actually going to jump from one layer to the next. On the other end, while I'm on that first layer, I just jump from one side to the other on the first layer. When I come over here, I jump from the first layer to the second layer, and I go around and around and around. Obviously, we want to, well, maybe not obviously, we're then going to join all the lines together. One of the goals, the end product, the deliverable of this process is one 3D polyline. AutoCAD likes 3D polylines. I'm quite comfortable with 3D polyline for setting my CNC router where it needs to be. So I'm going to take all these line segments, join them together, put in some proper fillets in there, I get a nice smooth contour all the way around. Again, for our particular case, running to the Axes router, it likes a DXF file. That's a pretty translatable file among CNC, so spitting out a file format that will work. So, next. What do I need to do? Well, I need to finalize this process. I need to make it more consistent. This is my work. This is just what I've done so that I can understand. I've not yet found a way to bring this directly to student learning. Students that are ambitious enough, I'll be glad to share this information. I have my stuff all over the shop, and I like to show people, and hopefully get them a little excited about it, but I haven't found a way to actually move forward with it necessarily. I do want to do one of the things that I talked about, which is creating various neck profiles. Oh, by the way, you'll notice my guitar case here.
We were wondering.
With my short scale base. So a 29-inch scale base fits in a common guitar case. You don't see a lot of these things, you know, but I love this thing. By the way, I love the big green poplar streak down the back. It's very natural. But this, you know, this geometry allows us to do things like this. They're short scale base. Not everybody can handle. Not everybody wants to handle a big 34-inch scale base, so a short scale base. V geometry on the neck, C geometry on the neck. Heck, short scale guitars if you want. Talk about mandolins and banjos. When you can make your own neck, you can make pretty much anything from there. Want to utilize the process with guitar bodies? Well, I got a little ambitious, and so I started. So I got a couple of models. So same thing that I did with the neck. I just map out my contours, both the top plane, the bottom plane. I find the curves that make that happen. I divide the curves, and then I send the tool around and around and around and around. The one that you're seeing right there, I actually have cut out of wood. And I brought the wood one because, I mean, foam is telling. It tells you something, but you can actually see the resolution a little bit better on the wood. So if you want to scope this one out, you can as well. And then once I had success with that one, I had another project I was working on, and I said, well, you know, I wonder if I can do 3D contouring on that one. So there you go. You know, I mentioned to you that there were some challenges if you go from one type of contour to the next. And when we were doing the next, it was all the four contours I told you about that we were joining together. When you look at those guitar bodies, not these don't apply because it's all lines around the outside. When you look at the guitar body, those guitar bodies that are going around, they feature something that's called a forearm relief on the front, and on the back they have a belly cut. And in those cases, pause back up. In a lot of cases with your guitar bodies, you're going to find that there's a fillet or a round around the perimeter. And that's fine if that's what you want. But when you get to the forearm relief, it's usually more of a straight line. And so again, if you take a look at that guitar, you'll find that the contour is no longer this rounded edge. It's a straight line. Same thing with the belly cut on the back. The challenge comes in if I have a round on the top and a round near the bottom. How do you go from a round to a flat to a round? And it's not very easy. What I found is that it takes trial and error because you end up with bumps where the curve sucks into the flat and you have to adjust that. So it's important, I find, when you develop these things to save revisions along the way. If I have a set of curves right here that I need to adjust, I don't need to go back and redraw the whole thing. I can start with a given revision and just focus on one area and smooth out the curves a little bit better. What else do I want to talk about? Oh, computer-aided manufacturing. Somebody in this room might be saying to themselves, well, don't they have software that'll do that for you? Why on earth did you spend, by the way, 24 hours to write out the geometry on that guitar body? Why would you spend 24 hours to develop this when software would do it for you? Again, I want to know that I can. CAD programs are good, they're well-intentioned, but the fact of the matter is, CAD program is a starting point, right? A computer-aided software is going to do what it thinks is best to make that project. But once I've got it in production, if I need to lean out a second or two, I take a look at my CAD program and say, what can I do to tweak this thing? Now, I'm working in reverse. I wanted to know I can do it, so I did it manually. But I will run the program in CAD and I'll see what it tells me. I'll see what I like and what I don't like, and we'll take it next. What else can I tell you? Any questions?
You said 24 hours to break the...
It took me 24 hours to design that guitar body. If I was going to do it again, it would probably take me about 6. So every time I do it, obviously it gets faster, the quality's a little bit better. So I took a look at the top. I have no idea. It felt like it went really fast. I have no idea how fast that was.
Food